Hello everyone, welcome to Physical Science. My name is Dr. Craig Carrigee and I'll be your instructor for this course. In this chapter, we're going to discuss science and its general purpose and principles, the way that science is used in society and the way that it's misused in society. We'll talk a little bit about how we're going to measure things throughout the course of the semester and how scientists measure things in general. And then we will get into some more specific things, such as metric prefixes and standard metric units, as well as understanding the scientific method, as well as other concepts related to the nature of science. When we talk about the nature of science, in my mind, it comes down to two basic ideas. The first is to be able to understand the natural world around us, understanding what's happening to us. Ancient people would have seen things like hurricanes and tornadoes and not understood why those things were occurring. And science is used to understand those things and to now predict them. But in general, not only is science used for that, but it's used to communicate between people. I always try to tell my students, if an alien came down to the earth and spoke none of our languages, how could we speak to them? And that would come from something like science. They may use different numbers or measurements, but they would still understand. If they traveled to the earth, they'd have to understand the concepts of gravity, the concepts of light speed motion. Physics and general scientific concepts would be the same for them as they are for us. And that's why it's important for us to understand them. In a way, science is our path into the universe. So when we talk about communicating science with one another, or being able to communicate it to an alien civilization, we have to understand how we can communicate general ideas. And we're going to be communicating general ideas about things, how fast something falls, how fast something travels. And those things include objects. Those objects have particular properties associated with them. Objects are things that we can hold in our hands, we can see and touch. And every object that we can hold or see or touch has some property associated with it. Has a shape associated with it, has a particular mass, it feels a particular way in your hand. It might move, or there could be a solid piece of metal, or it could be something like a slinky. Okay, so these things have particular properties associated with it. The problem comes about when we try to communicate that to other people, because those things that we say may be meaningless to someone else. First of all, if you go to another country and try to speak to someone in English, they may have no idea what you're saying. If you say that's a blue table, they have no idea what blue is in English, maybe. So how do you tell them something about the table that they will understand, regardless of what language they speak? We do that by assigning particular properties, what we call units, so that we can measure them and have a standard to relate that measurement to. In America, for example, if we measure the length of something, we generally measure it in inches. Anywhere else in the world, they measure it in meters. But we can convert inches to meters, and from that we could still communicate something like the length of a table. Maybe in that way you couldn't communicate the color, but if you somehow knew the wavelength of the reflected light of that color, you could still tell the person that color of the table in any language. Now, there are standard units in both systems, in the English system that we use here in America, and in a few, very, very few other places in the world. I invite you to Google where those other places are and find out how many you've heard of. But in general, in science, the metric system is what's used. The metric system has base units. When measuring things like mass, we use kilograms. But although you won't find the English system used in many other places, it is common to us, and we can relate it very easily. If someone told you their height in feet or their height in centimeters, you would immediately know the height in feet, and that's just because of the place that we live. But the units in the English system are based off of dimensions related to things like the human body, feet, yards, and they don't really relate to one another very well, very systematically. Right, 12 inches in a foot, 3 feet in a yard. I'm not sure how many yards are in a mile off the top of my head, but I know there's 5,280 feet in a mile. Could figure the rest out. So it's not a very convenient system to use when you're measuring multiple things of multiple sizes and at multiple scales. Instead, the rest of the world uses the metric system. The metric system uses particular standard units, standard base units. For example, the unit for length is meters, the unit for time is seconds, the unit for mass is kilograms, temperature is measured in Kelvin, as opposed to Celsius or Fahrenheit. And all of the other measurements that we have derive from these particular units. If we measure something like speed, speed is distance, which we measure in meters, over time, which we measure in seconds, derived from that particular unit. The beauty of the metric system, too, is that we can relate small things to large things by using only powers of 10. So there are 10 millimeters in 1 centimeter, 10 centimeters in 1 meter, 1,000 meters in 1 kilometer, and so on. And we can use prefixes on the measurement to determine a particular level of measurement. And honestly, it's a lot like we do with computing power. If you know the size of your hard drive, right, it goes from megabytes to gigabytes, which is 1,000 megabytes, to a terabyte, which is 1,000 gigabytes, give or take. And computers are a little bit different, but the concept is essentially the same. It's a relatable unit each time you step up. The great thing about these standard units as well is that we can use things like physical constants to actually set a particular number for them so that that value is meaningful. For example, the speed of light is a constant. Light travels at the same speed in a vacuum regardless. So we can use the speed of light to determine the length of a meter by basically just determining how fast light would travel through that 1 meter. Similarly, cesium atoms generate really fancy atomic clocks that are relatively precise, and so we can use those to determine how long a second is, with 1 second. It's related to a number of oscillations of a cesium atom. Finally, in your textbook, the standard unit for mass is set by a particular cylinder in France. So there was this small metal cylinder in France inside of these big fancy things, and that cylinder represented what 1 kilogram was. It was 1 kilogram. Up until recently, that was the standard for kilograms. It was not based on a physical constant. However, over time, the cylinder did lose a little bit of mass. And so to determine an atomic measurement of that cylinder, scientists used a particular physical constant. Much like the speed of light, they can be set up at a particular value that's known very well, and use that to essentially derive the measurement of a kilogram from that. And so now there is an atomic set measurement of a kilogram not related to that one particular cylinder in a thing in France. If you're interested in some more information on that, I've attached a related news article. So as I said before, beyond being able to use it to communicate to another person or another civilization, there's also things that we can learn from science. There's things we can learn from measurements. And so these things that we learn, or these things that we observe, we can combine them all together and consider a broader understanding of the world in general. For example, we can collect a ton of data about everything, right? And that's constantly done now anyway. There's constantly something measuring temperature values outside. Those constant measurements of temperature values and water levels in the sky, those values are used for weather predictions. And they can use that to predict where storms are going to come through, or when, and how severe they might be. People on TV use data about what you watch to determine what you might want to watch. Facebook does it all the time, as well as a bunch of other social media apps. Data can be predictive if it's used correctly. Similarly, relationships between data can be useful if used correctly. One prime example of that would be measuring the density of an object. The density of an object is based off of what are essentially two fundamental quantities, mass and volume, how much stuff and how much space you take up. Volume is a derived quantity of length. Height times width times length will give you volume, so 3 length measurements. But when we measure the density of something, we measure its mass divided by its volume. Any substance that's the same substance is going to have the same density. So 2 samples of gold, regardless of their size, will have the same density. 2 samples of iron or tin, and you could use the density of those materials to tell the difference between them. Density is essentially an intrinsic characteristic of a particular material. And there are other intrinsic characteristics as well. So the way that we can use this to be predictive is if we know something, say, about how weather variables interact. Let's just say, for example, we know that if there is some amount of water in the air and the air is some amount of temperature, that it's going to rain. And we multiply the two to get that value. This is just an example. That really wouldn't work. Well, then we could generate an equation from that by saying the water times the temperature equals whether or not it rains. So if we know one or the other, we can figure out the third. Or if we know 2, we can figure out the third. If we can constantly measure the temperature and the water in the air, then that can tell us, hey, it's going to rain, it's not going to rain. Now, that multiplication example is just an example, but it's very similar to how weather forecasts are done and the way that they use computers to run multiple models and compare them and generate a prediction. So many models it rained and so many it didn't. 70% chance of rain. And so scientists do that. They use symbols and they use equations to relate variables that they can then use to relate data that's observed and either make predictions or inferences about what might happen or what had happened. These equations can describe mathematical relationships. For example, if you measure the time that it takes for an object to fall a certain distance, you know the distance, you know the time, and you increase the distance and you keep measuring the time, you'll find that as that object falls, it falls faster and faster over time. You'll find that the relationship between the distance and the time varies at a constant value when you have distance versus the time squared. And from science, we can use that to determine that an object is not only accelerating as it falls, it's accelerating at a constant rate. And we can even measure the constant rate at which it's accelerating. So science really began sometime around the mid-16th century with scientists like Galileo and Isaac Newton. Galileo and Newton had some very similar ideas, and a lot of their ideas complemented one another. Galileo determining the way objects moved, determining that moons orbited Jupiter, and observing directly 4 moons orbiting Jupiter, and not the Earth like a lot of everyone else thought at the time, that everything revolved around the Earth. Newton did a lot of work with gravity and with motion, the ideas of forces and acceleration. Newton invented calculus to describe all these things that he was discovering. Before them, scientists just thought about stuff. They would think, hey, that heavy thing sure looks like it falls faster than the lighter thing, so that heavy thing must fall faster. That's what it looks like. So that's true. We don't need to test it out. Let's just assume that's what it looks like. That must be what's going on. And it wasn't until thousands of years later that people decided to try something different. And from that, learned enough to do things like put men on a moon. A lot of that progress, though, began with Galileo. He decided that instead of just thinking about things, he was going to test some of those things out. And he used experiment to do that. And through his ideas, generates what all scientific experiments still use today, which is known as the scientific method. In the scientific method, a scientist or a person sees something in nature. They observe something, and they want to understand what's causing that thing to happen. They think they know why that might be happening, but they're not sure. But there's a way to measure it. There's a way to determine if this is what's going on. And so it's tested, and you compare your findings to what your ideas were at the beginning and see if they support one another. If they do, good, move on to the next thing. And if they don't, revise what you were thinking. Try again. The basic general idea of the scientific method is that we observe something that we want to understand, and we have an idea of what that is. Most of you were probably thought that a hypothesis is an educated guess. I hear it every single time I ask my classes that question. But it's not just an educated guess. Sure, that's part of it. But it has to be something that you can actually test as well, something that you can actually do and figure out if that's the case. I mean, you can't observe that the sky is blue and say, my hypothesis is the sky is blue because of a 1,000-year-old man named Pete who lived here, and that's it. There's no way to test that. It's completely absurd, but there's also no way to test that at all. And so a hypothesis is a testable idea, a testable way of determining if there's a relationship between two variables. So you see something that you want to understand, you generate this hypothesis, and then you measure what you need to measure. You try to make things as equal as possible with only the difference being the thing you're trying to observe. If you want to know if different soils affect the height of a plant, you use the same plant, you use the same water, same place. The only thing that's different is the soil. And that will tell you if the soil is changing how the plant grows. Once you've done and observed your data, you compare the results to what you thought you would see at the beginning and refine your thinking. Either it supports your hypothesis or it doesn't. And that's how all of science continues. So we observe something in nature and we generate a hypothesis. And then we use an experiment to test that hypothesis, where we do something, recreate an event over and over again, drop objects and measure how fast, or measure the distance that they fall and the time that it takes. In general, some experiments will have controls, like we discussed just a moment ago, in terms of a plant, the amount of water, the type of plant. But those controls are things that are kept the same, with only the experimental part being the part that varies. So, for example, if we're measuring the plants, we could have a control group where we have plants that all have the same amount of water, but they all have the same amount of soil. And then we have an experimental group where we're changing the soil in each one, but everything else stays the same.